Hello, and the most wonderful welcome to all of you, my fantastic viewers, joining me on this journey across the cosmos today. It is an absolute joy to have you here. Before we embark on this incredible adventure to a world beyond imagination, I want to take a sincere moment to send out a genuine wish for you and your loved ones. In the vastness of our universe, your health and peace are the most precious things we have. So, from my heart to yours, I truly hope this message finds you feeling strong, positive, and in the very best of health. May your days be filled with energy, happiness, and wellness. Now, let's all take a deep, calming breath together and get ready to travel to one of the most astonishing places ever discovered. So, let's talk about a place that sounds like it was dreamed up in a science fiction novel, a place so bizarre and so extreme that it challenges everything we think we know about planets. Imagine a world where the ground beneath your feet isn't rock or sand, but something infinitely more precious. Imagine a planet where the very fabric of its being is crystallized carbon, a world that is, for all intents and purposes, a giant diamond orbiting a distant star. This isn't a fantasy, this is a real place, and its name is 55 Cancri. Also known as Janssen, this planet is one of the most fascinating and extreme exoplanets, planets outside our solar system, that astronomers have ever found. Its very existence pushes the boundaries of what we thought was possible and opens up a window into the incredible diversity of worlds that are waiting to be discovered in the great expanse of space. The story of 55 Cancri E is a story of modern astronomical detective work, of piecing together clues from starlight to unravel the composition of a world we can never visit, and of understanding the violent, high-pressure processes that can turn common elements into something truly spectacular. To truly appreciate the wonder of this diamond planet, we first need to understand its home. 55 Cancri E orbits a star called 55 Cancri A, which is located about 41 light-years away from us in the direction of the constellation Cancer. Now, 41 light-years might sound like an unimaginable distance, and it is, but on the scale of our galaxy, which is 100,000 light-years across, it's practically in our backyard. This star isn't alone. It's the primary star in a binary system, meaning it has a companion, a small red dwarf star, and together they dance through space. The 55 Cancri system is a busy, crowded place. We know of at least 5 planets orbiting 55 Cancri A, making it a miniature solar system of its own. The star itself is very similar to our own Sunday. It's a G-type main sequence star, just a little bit smaller, lighter, and less luminous, but otherwise a very close cousin. This similarity is important because it tells us that the raw materials that went into forming its planets were probably very similar to the stuff that made our own solar system. But the results could not be more different. The planet 55 Cancri E is the innermost planet in this system, and its location is the first clue to its extreme nature. It is incredibly close to its parent star. To give you some perspective, the planet Mercury in our solar system is the closest planet to our Sun, and it takes about 88 days to complete one orbit. 55 Cancri East is so close to its star that it completes a full orbit in just 18 hours. Yes, you heard that right. A year on this planet, the time it takes to go around its star once, is less than one Earth day. It is so close that it is tidally locked, meaning one side of the planet permanently faces the star, locked in a blazing eternal daytime, while the other side is turned away, forever in a frigid and dark night. The proximity to its star means the conditions on this world are nothing short of hellish. The dayside temperature is estimated to be a scorching 2,700 degrees Celsius, which is hot enough to melt iron, platinum, and even most rocks into molten lava. It is a world of fire and brimstone, a superheated cauldron where you might expect to find only boiling oceans of magma. So, How did astronomers go from discovering this hot lava world to theorizing that it could be made of diamond? The answer lies in brilliant detective work and the careful analysis of light. We can't see this planet directly. It's too far away and too close to the blinding glare of its star. Instead, scientists use two main techniques to find it and study it. The first is the radial velocity method, also known as the wobble method. As a planet orbits a star, its gravity doesn't just keep the planet in orbit. The planet's gravity also tugs on the star, causing the star to wobble in a tiny, little circle. By carefully measuring the subtle changes in the color of the star's light caused by this wobble, an effect called the Doppler shift, astronomers can determine the planet's mass and orbit. The second method is the transit method. If the planet's orbit is aligned just right from our perspective on Earth, it will pass directly in front of its star, causing a tiny, periodic dip in the star's brightness. By measuring the depth of this dip, scientists can calculate the planet's size. For 55 Cancri, we know it has a mass about 8 times that of Earth and a radius about twice that of Earth. This makes it a type of planet we call a super-Earth, a planet larger than Earth, but smaller than the ice giants Uranus and Neptune. But mass and size alone don't tell you what a planet is made of. You need to figure out its density. Density is the mass of an object divided by its volume. It's a crucial clue to composition. Imagine you have a box. If you fill it with feathers, it will be very light for its size, low density. If you fill the same box with rocks, it will be much heavier, high density. If you fill it with lead, it will be incredibly heavy, very high density. By knowing the mass and size of 55 Cancri, astronomers calculated its density. They found it to be surprisingly dense, but not as dense as it would be if it were a rocky world like Earth, which has an iron core. This was the first puzzle. The numbers didn't quite add up for a standard Earth-like composition. This is where the star itself provided the next big clue. Remember, planets form from the same cloud of gas and dust as their star. By studying the light from the star 55 Cancri A, astronomers were able to determine its chemical composition with great accuracy. They found that this star is unusually rich in carbon and has a very high carbon-to-oxygen ratio. In our solar system, the Sun has more oxygen than carbon. This means the planets that formed here, like Earth, are made mostly of silicates, compounds of silicon and oxygen, and metals like iron. We are literally made of star stuff that is oxygen-rich. But around a carbon-rich star, the planets would form from a very different recipe. In a carbon-rich environment, the chemistry of planet formation changes dramatically. Instead of silicon and oxygen combining to make sand and rock, silicates, carbon becomes the dominant building block. Think about what happens when you have a lot of carbon under immense pressure. Here on Earth, deep underground, carbon atoms subjected to incredible heat and pressure can arrange themselves into a crystal structure, creating diamond. Now, imagine an entire planet that forms from this carbon-rich material. A significant portion of its interior, under the crushing pressure of its own gravity, could have crystallized into diamond. That is the leading theory for 55 Cancri, based on its mass, radius, and the knowledge of its host star's composition. Scientists have modeled its interior. They believe it likely has a rocky silicate layer, much like Earth's mantle, but beneath that, instead of a molten iron core like Earth's, it could have a gargantuan layer of crystallized carbon. A diamond layer that could be thousands of kilometers thick. This isn't a single, flawless gem the size of a planet. It's more like a massive, compressed matrix of diamond mixed with other forms of carbon, like graphite. But the sheer volume is what is mind-boggling. The estimated diamond content could be worth mind-numbing sums of money, but of course, it's utterly inaccessible to us, a treasure locked away in a star system 41 light-years distant. on a world with surface temperatures that would vaporize any spacecraft in an instant. The environment on this world is as extreme as its composition. The side of the planet that permanently faces its star is a superheated wasteland. The surface is likely not solid in the way we understand it. It could be a global ocean of bubbling lava, or perhaps a surface covered in a constantly flowing river of molten rock. The atmosphere, if it even exists in a stable form under such intense stellar radiation, would be thin and probably composed of vaporized rock and other volatile elements. The night side, forever in darkness, would be unbelievably cold, a stark contrast to the inferno of the day side. There might be no meaningful atmosphere at all, as it would likely freeze solid on the dark side. The planet itself might be geologically active, with volcanoes spewing carbon-rich material, or its diamond interior might be incredibly rigid. The gravitational pull on its surface would be about twice what we experience on Earth, so if you could somehow stand there, you would feel crushingly heavy. The sky would be dominated by its enormous parent star, a huge blazing ball of fire that never moves in the sky, forever fixed in one position, pouring down lethal amounts of radiation and heat. The discovery and ongoing study of 55 Cancri e is a testament to human curiosity and ingenuity. It shows us that the universe is far stranger and more wonderful than we could have ever imagined. It forces us to expand our definition of what a planet can be. We have gas giants, ice giants, rocky worlds, and now we must add carbon planets to that list. These diamond worlds were predicted by theorists before they were found, and 55 Cancri e is the first strong candidate that fits the bill. It teaches us about the diverse outcomes of planet formation. The slight chemical differences in a protoplanetary disk, a little more carbon here, a little less oxygen there, can lead to the creation of entirely different classes of worlds. It makes you wonder what other wonders are out there waiting to be discovered. Could there be planets made of sapphire or other exotic crystals? The possibilities are as endless as the universe itself. While we will never set foot on 55 Cancri e, its existence captures our imagination. It represents the ultimate unattainable treasure, a symbol of the incredible wealth and variety of the cosmos. It is a harsh, violent, and beautiful world, a diamond forged in the crucible of a star's fierce embrace. It reminds us that our own planet, with its perfect balance of temperature, water, and atmosphere, is a rare and precious gem in its own right. The story of the Diamond Planet is more than just a cool fact. It is a chapter in the grand story of our quest to understand our place in the universe. It shows us that by looking up at the stars and asking questions, we can uncover secrets more dazzling than any fairy tale. So, the next time you look up at the night sky, remember that twinkling in the darkness, in the constellation of Cancer, is a star with a secret, a hidden world of fire and ice, where the very ground is made of diamond.